Okay, thank you very much. I will present, I will talk about some aspects of the work I have been doing for a couple of years now with Noema Nicolussi. It concerns the asymptotic geometry of Riemann surfaces and the moduli spaces, specifically some geometric new mathematical phenomena, new geometric phenomena, which appears close to the boundary of the compactification of the Riemann-Fold compactification. You don't see it in the title, but this is really the aim of the talk. It has something to do, hopefully, it's with the thematic of the workshop, in the sense that just before the pandemic, Bertrand Hénard and myself, we were lecturing just before the pandemic. We were lecturing in Lyon about related mathematics, and then we said that okay, we should talk about a possible connection between the two subjects. But then the pandemic came, and we couldn't discuss. Thank you very much for giving me the opportunity to present this work, and hopefully we will see there will be some non-commutative features which show up. We use a lot of recursions, and there are a lot of spectral theory we would like to understand. I hope that it will be clear that some of the questions will be related to the thematic of the workshop. But specifically, I would like to emphasize on this new geometric phenomena, which concern the sort of multi-scale, analytic, algebraic, and combinatorial polyhedral geometry. So I would like to spend some time. So there will be, I think, a lot of new terminology, new mathematics. Please stop me, okay? So even if I would like to go slowly. If it's okay if I don't finish my slides, please stop me if something is unclear. I will be happy to discuss it, and hopefully, I mean, it's usually this about these type of things. If there is a question, it means that it's a nice question. It usually gives to maybe some nice discussion and so on. So I will start my talk by giving motivation through the asymptotic geometry of Riemann surfaces, pose some of the questions, and then I come back to this higher rank Voronoi tilings, which is more combinatorial aspects of the theory related to polyhedral geometry, tropical geometry, and these kind of things. Okay, some specific feature is this hybrid geometry, which is a mixture of different sort of geometry. So some specific aspects is mixing complex geometry with tropical geometry, and going even in tropical geometry going beyond the developed concepts so far. Okay, so let me start by motivating so probably if you have thought about Riemann surfaces, probably you have some specific questions in mind about the asymptotic geometry of Riemann surfaces. If you are a physicist, you're interested in physics, probably the most interesting question is the connection between string theory and quantum field theory. But let me start with so it will be close. I mean, it will be related to this type of questions. But let me start by very, very basic questions. Okay. So the idea is to describe asymptotic geometry of compact Riemann surfaces. So let's ask very, very basic questions. For example, you can consider the Laplace operator, which acts on functions over the Riemann surface, but which gives us 1-1 forms. And these 1-1 forms, you can view them measures. You can view this as the Laplace operator, which transforms functions to measures. So you can ask, what is the asymptotic geometry of, what is the asymptotic of Laplace operators on Riemann surfaces when they approach the boundary of the moduli spaces? Okay, so these types of questions you read, this is with respect to this last phrase. So once you have answered this, then you would like to answer what is the behavior of the solutions of the Poisson equation close to the boundary of the moduli spaces. Okay, so limits of the canonical measure. So some types of measures you can associate on Riemann surfaces. You can define also on moduli spaces some sort of canonical measures. You would like to understand what is the behavior of these measures on Riemann surfaces, and also maybe if you have a measure which is defined on moduli space, you would like to understand what is the behavior of this close to the boundary of the moduli space. So some specific functions which are related to string theory are these green functions. So you would like to understand what is the asymptotic behavior of green functions close to the boundary of the moduli spaces. And if you're interested in algebraic geometry, you would like to understand, this is maybe the main thematic of tropical geometry, you want to understand what is the algebraic geometry when you go to this limit, which could be viewed as a tropical limit when you approach the boundary of the moduli spaces. Okay, so let me just, maybe I would like to spend a couple of minutes to precise 2 or 3 of these questions, okay? So it will be short, but it will give you an idea. So the canonical measure on Riemann surface, so it's defined by the help of a Hermitian product on the space of holomorphic one-forms. Okay, so these are the things that we have seen also in other lectures. So you take two holomorphic one-forms, then you can define a pairing between these two by taking alpha wedge the complex conjugate of beta. It gives us a 1-1 form. Then we can integrate over the full over the Riemann surface. If you normalize it correctly, it gives a Hermitian product, and then the corresponding canonical measure is defined by taking an orthonormal basis with respect to this Hermitian product. You take the sum and normalize it to get a probability measure. Okay, so the first question was about asymptotic of these probability measures when the Riemann surfaces approach the boundary of their moduli spaces. So green functions, so specifically hierarchical of green functions are defined over the
These measures are on different spaces, as you
exactly. So that is the first question. What does this mean? Exactly. So what does this mean? Okay. So I think I don't. It takes some time to discuss this. Absolutely. So this is the first. I mean, even formalizing all these problems is not. It's part of the solving the solution. Exactly. So this hierarchical of green functions, so they are defined in terms of this Poisson equation. So this is the Laplace operator. So you would like to find a function which will have which will not be differential, which will have a pole, simple pole, along the diagonal, and it is defined. It's a solution to this Poisson equation. But it's not unique. If you do this normalization, then you get a unique solution. So this is very important because it gives rise to whole sort of invariance associated to Riemann surfaces. I think one of the people who really put this into the perspective of study of Riemann surfaces with applications was Faltings, who defined this delta invariant, which was used in order to prove Mordel's conjecture. And it appears also in physics in the formulation of string theory, because the amplitudes in string theory are defined by the help of these green functions. And other string theorists use also these green functions to define other types of invariants, which they call modular graph functions. And specifically for this question of understanding topology, quantum field theory limit of string theory, it is important to understand what is the asymptotic of these green functions. Specifically for the purpose of this talk, if you're interested in algebraic geometry of the Riemann surfaces, you know that by tori theorem, the Riemann surface as an algebraic curve, it is defined. I mean, it is characterized by its Jacobian. So the Jacobian is defined as so you associate to any Riemann surface the first homology group. This is just R power 2G. If G is the genius of the Riemann surface, you have this lattice, which is the homology, the first homology with Z coefficient. You take the quotient, so you obtain a real torus, which has dimension 2G. But actually, you can put a complex structure canonically by viewing this as the dual to the space of holomorphic forms divided by H1, and this isomorphism is given by integration. By integration along cycles. So you have a form, you integrate along cycles. So we saw also in the last lecture, so it was used, so it was not about cycles, but it was used, the integration along paths was used to define some sort of functions along. So this is the same type, but over cycles. And the Hermitian product that I defined for defining canonical measures put a flat metric on this Jacobian. So then one question about asymptotic is the behavior of this metric. So this is specifically the main purpose of the talk is to describe the asymptotic metric geometry of these Jacobians. Yes? Exactly. So that's why this is a 2G, a real 2G, but this has complex dimension G. Exactly. You use this to put a complex structure on the. this is thank you for. Okay, so asymptotic geometry of Riemann surfaces have been studied a lot, specifically from algebraic geometry because of this, the very, rich geometric aspects of the moduli space, but also through the lens of hyperbolic geometry. For example, this calculation of volume, which was done by Mirzahani, was used. One of the main ingredients was hyperbolic geometry, but now there's other proofs using topological recursion. But very, very maybe surprisingly, the asymptotic geometry analytic aspects of Riemann surfaces. Okay, so I think, how can I go? Yeah, analytic aspects, it's maybe less intensively studied. So I can maybe cite some sample of actually results which were done. You can find. So it's, I think maybe it's not exhaustive, but it gives you an idea of. So Wentworf was one of the pioneers who studied the asymptotic of degenerations of Arakhelov-Green functions in a very simple case where there is just one singularity appearing in the boundary. De Jong recently he obtained some results about the dominant term for one parameter families. And myself with Spencer Bloch, Jose Burgos, and Javier Frezan, we studied the convergence of integrand in the string theory to the one in QFT, the quantum field theory. Other people like physicists Green, Docker, Piolin studied these modular graph functions. Faltings, he realized that there are some specific phenomena related to graph theory and complex geometry, which is appearing for the study of the variations of Arakhelov-Green functions close to the boundary of the moduli space. And specifically for canonical measure, parallel to our work, Shiva Prasad in 2020, he obtained the limit of canonical measures on Riemann surfaces for one parameter families. So in a sense, so I think maybe a summary of the talk is that actually we manage, through the things that I'm going to describe, we managed to give a complete answer to all the questions that I stated in the beginning of the talk. So the rest of the talk is about to give you a sample of actually constructions and results that we get actually. So it's not possible to give an exhaustive presentation. I will emphasize on the case of canonical measures just to give you some feature of this, and then I will specifically work with the Jacobians. Okay, so let me just briefly recall, I think we saw already, and it was cited several times, the moduli space of Riemann surfaces of genus G is, as I said, it's a set of points of MG, or is isomorphism classes of compact Riemann surfaces of genus G. It has a complex structure. It has a complex manifold. It has a dimension 3G minus 3. It comes with an analytic family of Riemann surfaces. If you take a point, if you put the fiber, the corresponding Riemann surface, then you get another space. So this construction, you get what is called a universal curve, and this is as a complex manifold. It is defined over what is called these étoile charts, so over some specific open sets. And it turns out that MG is not compact, and so basically you need to compactify it by adding some new points. And this was done by important work of Delin and Montfort in the 60s. And basically what they did was to add some specific types of singular Riemann surfaces which have the simplest kind of singularities. And these singularities, as singular complex spaces, are defined by equations. Locally, they are defined by equations of this form, xy equal to 0 inside C2. So if you take the two coordinate planes, they intersect in a unique point, the origin, and you see the singularities that you see here are of this form. But in order to get a well-defined moduli problem to solve it, you need to impose the stability condition, which was also mentioned in the talk by Margarita. So here you have, so in the stability condition requires that the object has only finitely many automorphisms. So it doesn't allow this type of singular Riemann surfaces, where you see there is a Riemann sphere where you can rotate and you get an infinitely many singularities, automorphisms of this type of singular Riemann surfaces. So these are not allowed. So to any of these objects, you can associate a combinatorial object, which is really the heart of all the results you can imagine about the asymptotic geometry of Riemann surfaces, which is the corresponding dual graph. So it transforms the one-dimensional components of this singular Riemann surface to points. And if you see a point, it transforms it to an edge connecting this. You see that this is really the dual. There's a duality between these two. This is a combinatorial object, but we will view it as a geometric object. So there's a duality between these two. This is called the dual graph of this singular Riemann surface. Okay, so for all of the questions I stated for which were concerning the asymptotic geometry of Riemann surfaces, it turns out that there is some non-commutative feature which appears close to the boundary. What does this mean? It means that so if you are in the middle of the moduli space, it doesn't matter how you approach the point. If you have a point here, it doesn't matter how you approach the point from here, or from here. You always obtain the same result because this space of holomorphic bond forms behave continuously. So since, for example, for the canonical measure, it was defined with the help of these holomorphic bond forms, you always get continuity. You don't see everything seems to be continuous. It doesn't matter how you approach. You always, the solutions of Poisson equation, they behave also continuously. Everything behaves nicely. But it turns out that whenever you want to approach one point in the boundary, it really matters how you approach. For example, here you can start from this, and then you go in the direction of one of the strata, and then you turn, and you are right here. So it means that you had given a preference to first go in this direction and then approaching the point, or you can go you start from here and then go from in this direction and then go toward this, and the solution will be completely different. So this order is really crucial, and it gives rise to the definition of new combinatorial objects. So these are really the heart of the solution to these asymptotic geometric problems. These are called layered graphs. So and there will be a higher rank polyhedral geometry that I will just talk about in a few minutes. But what are these? Let me just tell you what are these graphs that you see here. So this one, you view it as a dual graph of the singular Riemann surface you're approaching on the boundary of the moduli space. But you see that it is colored. And the color, so I have put the color, this pink, it's purple color here, and the blue, and then the green. I have put an order on these ones. This is the order of approaching which stratum in the moduli space you're approaching. So these are, you remember, through this duality between singular Riemann surfaces and graphs, each edge of the graph corresponds to one of the singular points that appear when you approach the singular point. So it means that these purple edges correspond to the fastest appearing nodes. It means that at the beginning, when you want to approach the Riemann surface, which has, sorry. Okay, so it means that when you want to approach the Riemann surface, which has this dual graph, you go first in the direction of the stratum, which corresponds to these nodes appearing first. Okay, and then you go in the direction of this one, the second stratum, and then the direction of the third stratum. Okay, so I think I don't want to give the precise definition how it is related to this asymptotic geometry, but you can imagine having parameters associated to these edges, which correspond to these edge lengths that we saw also in the yesterday. And so if you're approaching a singular Riemann surface, this corresponds to the fastest, to the largest growing edge lengths to infinity. And then these ones correspond to the second largest, and these are corresponding to the slowest. All of them, of course, live at infinity because you are going in the direction of a singular Riemann surface. Some parameter is going to be 0 or infinity. I mean, so if you go to the log coordinates. So this is really this one. But this layered graph gives rise to three monochromatic graph. And the idea is that basically through this graph, you can construct you can construct for if you have 10 colors, you will get a collection of 10 graphs. And the way you view these ones is by contraction deletion, which are somehow the basic tools in this non-commutative geometry of a lot of results in combinatorial on combinatorial structures related to graphs are based in these two operations. So what you do is that basically, if from the point of view of someone living, for example, on this vertex, the edge lengths associated to pi 2 and pi 3, these are smaller, infinitely smaller than the edge lengths of the purple edges. So it means that basically the edge lengths for someone living in the purple planet, these edge lengths are equal to 0. So you just need to contract them. So you contract these ones, all these edges. Sorry, yeah, for the purple planet, exactly. No, yes, exactly. So this is the largest infinity. So you contract the purple edges, you get this new vertex. You contract the green edges, you get this one, and then all the other edges survive. So this is the first scale. So it's about multi-scale geometry. This is the first scale you see of this multi-scale combinatorial geometric object. The second scale, in the second scale, which concerns these blue edges, these ones are infinity. So you just get rid of them because they don't play any role. They are at scale infinity for this scale. So you just remove them. But the green edges now at scale 0 because they are infinitesimally small compared to the lengths of these ones. So it means that you have to contract these ones. So you do the deletion of the edges, the colors which appear, which are above, and the deletion, the contraction of the ones which appear below. So this is, you get this picture. Okay, so in order to solve this problem, we construct a refinement of the moduli space of the Delimontfort compactification, which is a mixture of the dual graphs, these ordered colored dual graphs, and the corresponding Riemann surfaces. Basically, what you do is that you just take the singular point and you replace it by an edge, and you give it a color. So you get an ordered partition of the edges. So here again, this has rank 3. There will be 3 different layers of infinity, and it comes with colors. So you get this geometric object. So this is a geometric object, but actually it's a multi-scale geometric object. And the Riemann surface parts are living at the finite scale. So they are complex. This is, on this level, you do complex geometry. On the other layers, you do tropical geometry, but there is also interactions between the layers. And that is really the heart of the solutions to all these problems. Okay. Which one? This one? This is obtained by contracting this green edge, because the green edge is at the third layer of infinity. If you contract it, it means that you identify these 2 vertices, you get this vertex, and this becomes a loop. Okay, so maybe just to emphasize the non-commutative feature of the film, I just give you what kind of solutions. So you can prove that over this moduli space of hybrid, this multi-scale tropical complex curves, you can extend the canonical measures continuously, and the type of canonical measures you get are the canonical measures on components and sums, weighted sums of canonical some Lebesgue measures on edges. Just to give insight of this non-commutative feature. So in this example, you see there are 2 colors. I have just swapped the red with blue. So red is dominant here, blue is after. So this is the second layer, but now it has become the first, and this is the second. And you see that the type of the measure is changing. So this is, so if in order to get the probability measure, you have to divide this by some factor, which is the genius of this. It has genius 6, because 2 plus 2 plus 1, 5 plus 1 cycle 6. So 1/6 of this is the total mass of this. You see that this one has the same measure on these Riemann surfaces, but the graph part has changed. Okay, and incidentally, this one, which has just one layer, has the same canonical measure appearing as limit. Okay. Yes.
Your side, so is that compact? So the space. Can you say something more about the compactification?
Yes, absolutely. So this is a compactification. It is a compactification. It is Hausdorff. It has all the nice properties, and you have you get a universal curve over this, which is this hybrid curve that you have put together, and then it turns out that you can do analysis on these objects. That's what we do actually. So what we define is the Laplace operator, which is a hybrid Laplace operator on these objects, which mixes the tropical tropical analysis with complex analysis. But there is other interaction. So that's a good question. I mean, we would like to do put. I mean. We haven't developed this as some sort of analytification of some objects. If this is your question, we know that tropical geometry is related to what is called non-Archimedean analytification, to Berkovich geometry. We know that complex analytic spaces are sometimes, if they come from algebraic geometry, they are analytification of algebraic varieties, and you would like to do the same thing here. So yeah, these are somehow related to some hybrid analytification. I think that is my conjecture, that there should be some hybrid framework in which these objects are really tropicalization of those hybrid analytic spaces, but we are not there.
It's not an orbifold, right?
Sorry?
This space itself is not an orbifold. This MG hub.
It is an orbit. I mean, it's an orbifold in this sense, because you can define. So on some specific charts, it's a product of the moduli space of some open set in the moduli space of non-homogeneous curves times some polyhedron, some open set in some polyhedron. Okay, I don't have pictures of the polytopes which appear. There are generalized permutation which appear locally, if you want to know.
But can it be also realized? Because so if I would be given an order to construct such a space, I would take some blow up along the boundary divisor of MG bar, and then inside this blow up, I would look for the parts where, okay, so I wouldn't need all blow up, because your way of distinguishing the nodes is much more coarse. But I would look for a part that would actually distinguish it according to your levels of infinity, and would find there some realization.
As a combinatorial object, you can view it as a fan, but the ordering and the geometry afterwards you do is it makes it a little bit different. So as combinatorial gadget, it's generalized permutation, so it's a fan, it's a sort of subdivision of actually this dual complex of the.
And it is not subspace of MG bar.
No, you have projection to it.
Not projection to it, exactly. So by forgetting this simplicial coordinate, it's a refinement. It lives above. Okay, so let's come back to the Earth. So I think I would like to now do some mathematics. Okay, so I'll just give you some hint of maybe do some So. Okay, so I would like, as I said, so the objective is to describe the metric degenerations of Jacobians. So it's really about the geometry of this tori, this real tori endowed with this flat metric, and you would like to say what happens when you go to the boundary of the Delin-Mumford compactification. But obviously, it's not. You don't need. I mean, the Delin-Mumford compactification is not is sufficient because of the things that I told you. You have to do all these. Extension into these layered objects, add this coordinate, and so on. But let me just, so it's related to some metric collapse phenomena, we'll see later, which were studied quite some time ago by, in the 80s by Gromov, then Fukaya, which is also related to this mirror symmetry, to this, what is called SYZ conjecture, and this kind of phenomena which are still actually the active field of research today. And it will be also related to higher rank polyhedral geometry, which was the subject of the PhD thesis of my PhD student, Hernan Uriart. So it is linked actually to these things, but it's somehow new. And let's ask the very basic questions. Okay, so this is really some very basic questions you would ask about. So it's about flat metrics on tori. So the flat metrics on tori is easy. You can, I mean, they come from a scalar product, because you can go to the universal cover, you get the scalar product. It's about the behavior of a scalar products when you go to infinity. What is infinity? I mean, it means that you have a family of scalar products over a fixed vector space, and you would like to study the asymptotic behavior of these scalar products. I think this is a very basic question. It's surprising that it hasn't been maybe been studied before, because it's really the type of questions you would probably ask. I mean, to be honest, I hadn't asked myself before working doing this, but I think it's very basic question. Describe all possible limits of scalar products on this. Okay, so this is symmetric bilinear form, which is positively finite. So specifically related to the tori, so this is, you have this lattice of full rank, which is a lattice of full rank, and then this gives you a flat metric on the lattice. And then you would like to study the induced metric on this torus, on this family of tori, if you have a family of scalar products when you go to infinity. What infinity means here will be precise. And more generally, what you do is that, this is a question related to this, because you have this universal cover, you can fix a fundamental domain, and this fundamental domain, you can choose it to be a Voronoi cell, so the set of points which are closest to a given point. So it's really about the behavior of the Voronoi cells. So if you haven't seen a Voronoi cell, if I give you a discrete set inside the space which has a metric, then you can decompose that space into regions. And those regions are defined by each point goes to the point in the discrete set which is closest. It's a fundamental actually construction in polyhedral geometry, in commutative geometry, which is used in many applications, in actual applications of mathematics. Okay, so the answer to this question turns out to be related to this higher rank philosophy that I described. So okay, so maybe I should have motivated a little bit, but yeah, I think I have 10 minutes or maybe something. Yes, it's a space of positively finite. Exactly. So it's about it's if you like to ask it properly, it's about natural compactification in the style of what I presented of that specific code. Exactly.
But classically, if you don't look at it, always can degenerate. Give me a billion.
Absolutely. So
But it will also show up here, or does it?
Absolutely. But it's a little bit. I mean, you have these neuron models and these kind of things, and then this is a refinement of those.
Yes, so level 0. So
Exactly.
Okay.
Exactly. And this is a higher rank version. I mean, if you want to do it maybe step by step, you would first of all modify the neuron model so that it considers also the geometry of this dual graph, which gives you this the torus that's associated to the graph. Which is h1 of the graph with r coefficients divided by h1 of the graph with z coefficients. But really, if you want to answer this question to get a nice space, actually, it's not going to be a compact space. But if you want to have a nice space which is good for the purpose of applications to analytic geometry, then you would do, I think, what probably this is the setup somehow. Okay, so. The answer is about inner products of higher rank. So I have to define you what it means for a space to be endowed with an inner product of higher rank. And the idea is that if you have a family of inner products, you see, okay, so there is a dominant, there's a dominant factor, which tells you that if you look at the norm of the vectors in your space, the space is fixed, and you see that in your family, some of the norms go to infinity faster than the other ones, okay? And then you take this, maybe you view it on a ball, on a unit ball, and you can normalize your family of vectors. You take the first limit, it gives you something, and you put it here. Okay, so this is the one. But this is not a metric anymore. This is not an inner product, because you might have some of the lengths could become 0, because these are not the dominant ones. Okay, and now what you do is that you restrict your family of scalar products to the ones which have become 0. You do the same procedure. You normalize it by new scale, and you take the limit. It gives you the second one, and then if you do it, it's a finite dimensional vector space. You get a family of bilinear forms, and this is basically the first candidate. Okay, the first candidate as a limit is a symmetric bilinear form, which is defined on h times h, with values inside R. And I have put a lexicographic order on RR because of the procedure that I just described. Okay, so this is more important. This is the dominant scale somehow. Okay, and that's the second one. Okay, so this is maybe you start from this, but then you have to see if we can develop some nice theory out of this. First of all, if you have something like this, and you can define a filtration, you define on this exactly by what I described. So this is the filtration you get by restriction. So these are the ones. F2 are the ones such that with respect to the first one, they are 0, so they don't see them. So it gives you this filtration. This is a sequence of real vector subspaces of H, which end up after R step to 0. So this comes out of any symmetric bilinear form that you can define on H. But this comes from, if it comes from a family of a scalar product, you have the positivity. Okay? And the positivity should survive, okay, so somehow. Okay? So it means that if you take an X, the length of X as an element of this ordered group should be non-negative, unless this is 0. Okay, so this is the positivity you like to apply. So this is the first candidate. But it turns out that this is not good because it gives rise to a lot of pathological examples, and the examples which come from analytic geometry, they verify some stronger positivity that I will define here now. This is this positive definiteness. So this is this positive definiteness of higher rank, and it is described as follows. So in addition to the positivity, you require that each component that you get here, so each component you can restrict it to Fi, to Fj, but on Fj plus 1, this bilinear form is 0. So you get a symmetric bilinear form on the quotient of Fj by Fj plus 1, and then you ask this to be positive definite. And this turns out to be the nice, the right feature because of specifically. Okay, so maybe I give you an example of how much time I have? 5 minutes. Okay. Okay, so maybe I tell you that one of the basic examples is this higher rank Euclidean inner product, which is obtained. So you take the same value group R, and then you put these multilinear forms. Okay, but this is an interesting. I mean, this theorem justifies the definition because it tells you that this is an inner product in the sense that I defined, if and only if for any sequence of for any family of vectors which verify this scaling property that I just motivated, the pullback of this inner product to H, which is defined by doing exactly, going back to, I had rescaled, now I put the scaling back. For any family which verifies this, eventually you get scalar products. So these two conditions are equivalent. So in a sense, these are really the limits of the scalar products. Okay, and it turns out that you can define orthogonality relations. So you can develop some sort of almost orthogonal linear algebra in this setting. You say that two elements are almost orthogonal if this property holds. That if you look at the product of these two, then the term which appears which has a lower scaling is 0. So this is the right, and you get this nice decomposition, almost orthogonal decomposition of H into spaces, H1, H2, HR, and these Hj's are isomorphic to Fj over Fj plus 1. So in a sense, what we have done by doing this filtration survives at infinity. You can see it as an orthogonal decomposition, almost orthogonal decomposition of H into vectors which live in different scales. Okay, but now I would like to, as I said, my motivation is to give to understand the metric degeneration of tori. I mean, this will be done in terms of Voronoi decompositions. But very basic examples show that the discreteness, the notion of discreteness is not good if you just put the discreteness with respect to the Euclidean topology, because for example, in this picture, you see that one of these Voronoi cells which appear is this one, which has 0 dimension, which has 1 dimension, sorry. And actually, you can construct examples of discrete sets whose Voronoi decomposition, if you define it like word by word, doesn't give you a covering of the space. There will be holes in the space. Okay, so then it means that this notion of discrete is not good. Okay, so then you have to define almost so admissible discrete sets. If you define admissible discrete sets, then you get nice decompositions. But again, in contrary to the case of Euclidean geometry, scalar products, the Voronoi cells will not be closed. So there will be parts missing. I mean, you don't see it here, but here it will be more clear. In this picture, you see that they provide a tiling of the space, but the Voronoi cells will be polytopes, but parts of the polytopes are missing, and this is still mysterious for us. What are the parts which are missing? Okay, so. And this is, so I didn't give the admissible discrete the definition, but it's related to a sort of topology that you can put on H, which mixes the Euclidean topology of the vector space and the order topology. This is the open sets are defined by taking an open set inside Okay, so maybe I skip this. It's a bit, but you see, it's a nice. You see that this is almost an open set, but there are parts missing in directions of. It's a polydisk. It's a polydisk in this new topology, and these admissible discrete sets, the ones which have a nice theory of Voronoi decompositions, are the ones which are discrete with respect to this topology. Okay, so maybe this is the heart of this study, is that actually basically any Voronoi cell that you define, if you have an admissible discrete set, admits an admissible decomposition as a Minkowski sum of polytopes, which are polyhedra, which are themselves Voronoi cells inside this Hj. So this is the almost orthogonal decomposition of H. Each vector in H decomposes as this one, as a sum of vectors which live inside these ones. And all the Voronoi cells, you can, using this almost orthogonal decomposition, you can decompose the closure of the Voronoi cell as the sum, as a Minkowski sum. I put this because these are almost orthogonal to each other, as a Minkowski sum of some Voronoi cells which live entirely inside these spaces Hj's, or translations of Hj's. Okay. So let's come back to the case of okay, maybe I skip this, but this is a tiling associated to this object, which doesn't have a complex part. This is a tropical curve of rank 2. It has 2 layers, and if you look at the minors, so the first minor, it consists of contracting this one. It gives you a cycle with with one vertex. It will have 2 loops with one vertex with 2 loops, and the corresponding Voronoi cell is just. You can see that this gives you the usual Euclidean product on the space, and it gives you this Voronoi cell. But when we view this as the second one is just an edge. It doesn't have any. H1 is 0, so there is nothing. And you see that, but this is more difficult. I mean, it's more tricky because some parts of the Voronoi cell is the sum of the 2 Voronoi cells. This Voronoi cell, but some parts are missing. Okay, I think I'm a little bit. I haven't yet. Okay, I have 2 minutes here. Okay, okay, so I can finish with. So the Hausdorff convergence of you have the. I mean, this is somehow the heart of the answer to this question of the convergence of metrics, is that basically also the scalar products can go to infinity. You have this appearance of higher rank. If you look at the Voronoi cells, if you have a lattice, so imagine that you have a lattice, then you don't have this compact Hausdorff convergence. If you take a lattice, then basically the Voronoi cells, with the metric induced by the Euclidean topology, they converge in the Hausdorff metric. So you have okay. So here it should be the closure, but this is also fine, I think. Yeah, the definition of Hausdorff. So okay. So if this is a compact space, for example, if you get a lattice, admissible lattice, which is a lattice which is admissible discrete with respect to this higher rank inner product. Then you have the Hausdorff convergence of these Voronoi cells. Okay, and then you have this collapse, which is this metric collapse, which tells you that from this metric, from this higher rank, you get a family of. I told you there is this filtration which is defined on H from the higher rank inner product. You have the lattice, then you intersect, and you define these tori, these intermediate tori. You take the quotient of these guys. And you have this Gromov-Hausdorff convergence of, if you take Tj with respect to renormalize, you have to renormalize the distance function on Tj by these factors. Then there is the convergence to this quotient tori with corresponding distance function coming from the jth part of this inner product, higher rank inner product. And interestingly, for the volume, you see if you scale the volumes correctly, you get this nice formula for which you can view it as a sort of, okay, sorry, maybe I don't comment on this. Let me just come back to the Riemann surfaces, why this is interesting, because it allows you to describe the asymptotic metric geometry of Jacobians. So this is a simple case where you have just two nodes appearing. So this is a family of Riemann surfaces which converge to this one. This is the dual graph. These are the vanishing cycles. From this, you get this filtration. This is the whole homology of this. This is a 2G dimensional space, as I said in the beginning. These are the ones which concern so there is a map from this to the graph, which consists of contracting these parts. So these are the ones which do not give any cycle in the graph, and these ones are the vanishing cycles. This is a basic example. So these are the three types of, and then you have this convergence of the Jacobian. In the very simple case where you have just one layer appearing, then you get, if you in one parameter family, then you get the Jacobian of these ones rescaled by the corresponding distance function coming from the polarization, which was defined on the holomorphic forms, converge to the Jacobian of this graph with the corresponding distance function. On the second layer, you have the same thing, but the scaling is now constant because this concerns these Jacobians of these components. And the other scale, you have to scale by the inverse of this scale, and you get the convergence to the dual tori here that is defined. And interestingly, you get the volume. Actually, there's no normalization here. The volume of these guys converge to the volume of the components, which is the product of the volume of each component. Okay, thank you very much. I think almost.